So here's a motivating question. So this is really quite different. Why do continuum equations like those of Navier-Stokes and Navier-Cauchy work? In treating systems like fluids and steel bars as continua, they completely misrepresent reality. They completely ignore any structure at lower scales. They just treat them as blobs all the way down to infinitesimals. So that suggests that there's a kind of strong conception of at least a relative autonomy of the equations from the actual lower scale details. So what kind of explanations could possibly be offered to explain both the continued success of these equations and this kind of autonomy? So I think there are two ways to study the bulk behavior, at least two, of many body systems, and perhaps one or both of these can answer the questions. On one approach, which is a sort of traditional reductionist approach, foundationalist approach, that it'll aim to predict and explain the continuum scale behaviors in terms of the fundamental theory that characterizes the components, the atoms, the molecules. On the other hand, one might employ a hydrodynamic or correlation function approach that privileges structures at scales between the atomic and the continuum. So the first approach is a kind of bottom-up approach and typically begins with the Boltzmann equation or even with Newtonian ODEs for the positions and velocities of individual particles. That approach has seen some success for systems that are relatively sparse, like dilute gases, and for which collisions and scattering events are rare, and free streaming is the dominant dynamical behavior. So can this approach explain the relative autonomy of continuum scale behavior from lower scales? I want to say the answer to that is no. Can that approach determine values for the parameters that appear in the continuum Navier-Stokes equations, like viscosity and density, or in the context of materials, and the Navier-Cauchy equations, the elastic moduli? Again, I want to say no. So what I would like to do here is present this second mesoscale first approach as a widespread general methodology in condensed matter physics and in materials science. I'd like to suggest that such a correlation function hydrodynamic approach can provide the explanations that we want. But before getting to that, we need to think how to properly understand the parameters, like the order parameters and the material parameters that appear in condensed matter physics, fluid mechanics, and materials science. And I hope that will begin to motivate the mesoscale first methodology that I'm interested in. So let's consider an example. If we came upon a lump of ferromagnetic material while hiking with the compass, we could determine its direction of magnetization. If we heated it up over our campfire, we could theoretically notice that above certain temperature, the lump is no longer magnetic. At that level or scale, we might believe that we've discovered a new quantity, the net magnetization M. And we would in fact treat M as a continuum parameter that's a function of temperature. And everybody knows that this is sort of the plot of the order parameter and how it changes with temperature. But at this level of observation, we would treat the parameter as a continuum quantity like pressure, volume, and temperature in the ideal gas law. But we know that the ferromagnet is at atomic scales composed of lots of atoms with spin magnetic moments, etc. And so from the point of view of atomic scales, from the perspective of what we take to be fundamental theory, we don't see the order parameter M at all. Really, M is defined as the difference between the densities of upspins and downspins at space-time points. And that's a quantity that is defined at scales considerably below that of everyday continuum scales and considerably above the atomic scale. It's a mesoscopic parameter. It allows us, in fact, to say an awful lot about the macroscopic nature of our many-body system, without having to know much detail at all about the nature of the system at its most fundamental scale. And as such, it reflects the kind of relative autonomy of the upper scale continuum behavior from the lower fundamental scale details that I mentioned earlier. Now, Michael Fisher believes that understanding order parameters in this way yields a profound conclusion about the structure of the world. He says, significantly in my view, Landau's introduction of the order parameter exposed a novel and unexpected foliation or level in our understanding of the physical world. Traditionally, one characterizes statistical mechanics as directly linking the microscopic world of nuclei and atoms to the macroscopic world of, say, millimeters to meters. But the order parameter as a dynamic fluctuating object in many cases intervenes on an intermediate or mesoscopic level characterized by scales of tens or hundreds of angstroms. So I want to stress that this is the traditional approach of directly linking is sort of the reductionist approach that I'm saying isn't going to be able to answer our questions. So the definition of the order parameter demonstrates that the parameter is actually coding for correlations between the spin components. Fluctuations in aggregates of the atomic components, the spins, lead to correlations. And we get a picture that looks something like this. You can think of the black regions as regions of upspins, etc. So they're correlated with one another. So now let's think about the Navier-Stokes equations. In these equations, we have eta is the viscosity of the fluid, F are the body forces, like gravity, rho is the density, and V is the velocity. The viscosity and the density are material parameters. Different fluids are going to have different values for those material parameters. They're definitive or constitutive of different fluids, right? They provide the material specificity. How do we determine their values? Well, primarily through experiments in a laboratory. These parameters, like the magnetization, I think, should be understood as mesoscale parameters too. They code for structures present at scales in between the continuum and the atomic. Now, I said earlier that the reductionist, foundationalist direct connection between atomic scales and continuum scales won't work. It won't work to determine the values for the material parameters. But a reductionist might reply, that's just wrong. It's really easy to make such direct connections. So consider the density. There's no density parameter in the theory of molecular dynamics, but we can nevertheless connect the molecular dynamics to the continuum theory and determine a value for the density. We can reason as follows. Suppose our molecular theory says there are n molecules per unit volume. We can determine average mass density as a function of position in the fluid and side length L of a small volume centered on X. That's going to be n over L cubed, and then we just take the limits and we get a density which is a function of the position X. And so we've solved our upscaling problem via volume averaging. So the procedure is just to look for lower scale analogs of upper scale parameters and then take the limiting averages. But unfortunately, this works only very rarely. And to see why simple volume averaging will almost always fail, let's switch from fluids to materials, and I'll come back to fluids and hydrodynamic descriptions in a little bit. So let's think about materials like steel, railroad tracks. At everyday scales, steel bars look reasonably homogeneous. If we look at it with our naked eyes or with maybe magnifying glass, we don't see a whole heck of a lot of structure. It appears to be uniform. But zooming in reveals structures that are hidden at everyday scales. And we get this picture that demonstrates that there's all sorts of structures at different scales within steel, and the steel exhibits different behaviors at different scales, which is characteristic of many body systems. In order to describe the dominant important features of steel at these shorter length scales, we introduced this concept of a representative volume element. And interestingly, this really wasn't introduced into the literature until the 1960s. So we have this idea, we have this point P, it's a material point, it's a continuum concept surrounded by an infinitesimal material element. Structures in the material element, the voids, cracks, inclusions, are to be treated as the microstructure of that macro material element. So evidently there are three scales involved here. There's the continuum or macro scale, big D, by which the neighborhood of the material point is characterized. There's the microscale, little d, that represents the smallest microstructures whose properties, and we'll see that typically shapes are the most important properties. are believed to influence the response to stresses and strains imposed upon the neighborhood of that material point. And there's also the lattice scale, the atomic scale. So let's consider a well-mixed composite, 50% of which is a good thermal conductor and 50% of which is an insulator. And suppose the red phase is the conductor. And just think about the leftmost picture here. The difference here is that the red phase is the matrix phase and the white phase are the inclusions embedded in the matrix. If we tried to infer the conductivity of the material by volume averaging, we would likely be grossly in error, right? If the red material is the conductor and the configuration was as it is on that left picture, then the material will be a very good conductor. If the red material are in the inclusions, then the material would be a terrible conductor. The reason, of course, is because the red material is connected and the inclusions are not. So volume averaging of the sort typically assumed in sort of reductive programs is not a good means for upscaling to determine continuum properties of systems. It's only going to work for systems that are homogeneous at the lower scales. So making direct connections between atomic and molecular level and the continuum level is not as straightforward as many reductionist programs assume. Okay. So our steel railroad track bends as the train goes over it. The way the track returns to its unbent equilibrium state is going to depend upon the relevant material parameters, the Lemay parameters, lambda and mu, in these equations, the Navier-Stokes equations. So what we're interested in now is these material parameters, lambda and mu, which are analogous to the density and viscosity in the fluid situation. These equations, just like the Navier-Stokes equations, treat the materials as continuous blobs. They're relatively independent or autonomous from the atomic details. They're relatively autonomous and not completely autonomous because the values for those parameters surely have to depend upon some lower scale details. And so what we're interested in is how can we determine the values for those material parameters given some knowledge of the lower scale details in those situations where it looks like we can't do the kind of direct volume averaging. So if the bar were homogeneous, I think I cut out a massive part of this. Yeah. So, all right, anyway, let me go on. Okay, so if the bar were homogeneous, then the relations between the stress and strain would be the following, right? We'd have the stress is related to the strain, where K is the material parameter of interest that describes kind of the bendiness of the beam. It's just like the spring constant in Hooke's law for elastic materials. Now, if we consider our bar as a heterogeneous system with a representative volume element as we had earlier, we're going to have a different problem. Given the heterogeneity of the bar, the stress-strain relation that we just looked at won't be correct. Instead, we'll have to find an effective equation for the actual heterogeneous bar, right? And so that's given in equation 5, where we take this average stress and relate it to the average strain with a new effective parameter. Those averages are volume averages defined by 6 and 7, and the effective linear stress stiffness or rigidity, K star, is determined by solving 5, given the averages 6 and 7. And that looks like a completely easy problem. Simply compute those volume averages and solve that equation for K star. But in order to perform that operation rigorously, we need exact solutions for the stress and strain fields. And that means that in order to upscale, we need to know an awful lot of more information about the structures in the relevant representative volume elements, a lot more than just the volume fractions. We need information about the geometry, the topology, the shapes, and connectedness of the structures in the RVEs. And we can represent this information using correlation functions. So let's consider a two-phase random medium, where V is the representative volume. We can define indicator functions or characteristic functions to decide which element, which phase we're in, whether we're in the red phase or the white phase. And then we can start throwing darts at this representative volume element. We can determine the limit relative frequencies that these randomly thrown darts land in various phases. Okay, so we can ask a bunch of questions about this representative volume element. What's the probability that the dart lands in the red phase? Well, that's going to be this limit relative frequency of the number of times the darts land in the red phase, and that'll give us the volume fraction. That's going to give us the volume fraction of the red phase. We can now throw line segments. What's the probability that 2 points in V separated by a line segment of length R are both, the endpoints are both in the red phase? We can ask what's the probability that an entire line segment of length R lies completely in the red phase? We can ask lots of questions. So what we want to do is start to throw darts to get certain information, throw line segments, throw triangles, etc., all to find endpoint correlation functions. So these are questions about correlations, as I said, and they can tell us about the shapes and connectedness of the structures in the representative volume elements. To determine the structure of those RVEs, we need a bunch of endpoint correlation functions with n going to infinity. So in order to determine the values for the stress and strain fields in our averages, we actually need an infinite amount of information. So exact upscaling is hard, even if we start at mesoscales considerably higher than the atomic lattice. Nevertheless, there are homogenization methods that may allow us to find a range of values for the effective material parameters like K star. And once we understand material parameters as coding for correlational structures, we can employ homogenization techniques to determine the ranges of values. And we can explain the relative autonomy of the continuum equations from fundamental lower scale details. So now let's switch back to fluids. So consider a fluid or gas in a cylinder that's received a push of short duration. As a result, there's going to be a pileup of molecules near the piston. The density of the gas then is going to be greater than it is farther away from the piston. And that pileup creates correlations among the gas molecules. Those correlations are then going to decay as the system returns to equilibrium. Now consider a fluid in equilibrium. From a statistical mechanical point of view, quantities like density are constantly fluctuating about their average values. The fluid could have gotten into such a non-equilibrium state by a spontaneous fluctuation away from equilibrium. Now, Kadanoff and Martin assert in a famous paper entitled Hydrodynamic Descriptions and Correlation Functions that the response of a system to an external disturbance can always be expressed in terms of the time-dependent correlation functions of the undisturbed system. More particularly, the linear response of a system disturbed slightly from equilibrium is characterized by the expectation value in the equilibrium ensemble of a product of two space and time-dependent operators. When a disturbance leads to a very slow variation in space and time of all the physical quantities, the response can alternatively be described by the linearized hydrodynamic equations. So there are two important consequences of this. On the one hand, we can understand the linear response of a non-equilibrium system in terms of the statistical mechanical characterization of the corresponding equilibrium system. And second consequence is that the responses can always be characterized using correlation functions. From the first consequence, it follows that equilibrium statistical mechanics itself has a means to describe at least some non-equilibrium behavior of transport properties in that slow linear regime. So we can characterize and describe and explain some non-equilibrium behavior in from a non-reductionist, non-Boltzmannian perspective. And that's the core philosophical consequence of the fluctuation dissipation theorem from statistical mechanics. From the second consequence, it follows that there have to be structures at mesoscales that those correlation functions are representing. Those structures are the gradients of conserved quantities like particle number and density and other transport properties. And so from the point of view of mesoscale modeling of material parameters, the representative volume elements in fluid contexts also represent correlational structures, just as we saw when we were determining the structure of RVEs in the materials case. Those are structures that reflect, for example, the pileup of molecules near the pistons or those created by fluctuations. So correlation functions code for natural parameters with which to examine the continuum scale behaviors of many body systems. That's what I want to claim. So just to recap what I've said so far, before I go on to try to make some connection with this conference by talking a little bit about machine learning and renormalization. What I've tried to do is to argue that there are mesoscale structures in between atomic or molecular scales and the continuum scales that play a key role in describing continuum behaviors. Those structures enable us to explain the relative autonomy of continuum theories from the atomic or molecular theories. And what we've looked at is a wide-ranging methodology in which mesoscale structures are privileged and are considerably more important for describing and explaining bulk behavior than our more so-called fundamental features of the system. This is a methodology that's widely known by physicists and material scientists, but virtually ignored, as far as I can tell, in the philosophical literature. So reductionist strategies that appeal to fundamental theory to describe and explain such behaviors, I think, are unlikely to succeed. All right, so now let me just try to say a little bit about what might be going on in some of the connections between renormalization group and deep neural learning using restricted Boltzmann machines, to the extent that I understand it. So there's been a lot of discussion about this connection, the relation between those two things over the last, say, 10 years. And I just want to make a comment about this relationship, its relationship to this mesoscale modeling that I've been talking about. Lin et al. In their paper, Why Does Deep and Cheap Learning Work So Well?, provide an answer to their title question. Their claim, essentially, is that neural nets are so useful, at least from the perspective of physics, because most of the Hamiltonians that we care about are polynomials that are local, symmetric, and of low order. And many of them can be expanded in power series as well. And if things are even simpler, if x can take only discrete values, like 1 or 0, or 1 or minus 1 and 1, we essentially get an Ising-like Hamiltonian. Now, in an influential paper, Maida and Schwab argue that there's an exact mapping between the renormalization group and unsupervised deep learning based on restricted Boltzmann machines. The idea is to find an effective, large-scale pattern of behavior in many body systems that are distilled from the noise present at microscopic scales. That's sort of what RG does. And that can be done via a kind of Kadanoff block spin scheme that reveals hidden spins that code for correlation structures, that code for correlational structures in the data, where the aim at each iteration is to preserve the structure of the free energy to the greatest extent as possible, to make the renormalized or the effective Hamiltonians look as much like the original ones as possible. And you get a picture that looks something like this. On the left, we have block spin or decimation a la Kadanoff. And on the right, with the deep architecture, we're essentially introducing hidden spins that capture the correlations among the ones at lower levels in the net. So I want to suggest that a fruitful way to think about this connection between deep neural nets and RG is in terms of discovering correlations in representative volume elements. It seems that the algorithms are determining the crucial geometrical and topological features required to represent the appropriate order parameters. In effect, I think that their algorithms are implementing Kadanoff and Martin's hydrodynamic correlation function approach to many body systems. One last thing. One point of contention between Mehta and Schwab and Lin et al. Concerns whether the algorithms are really implementing unsupervised learning. So Lin says, contrary to some claims in the literature, effective field theory and the renormalization group have little to do with the idea of unsupervised learning and pattern finding. Renormalization group procedures are essentially a feature extractor for supervised learning, where the features typically correspond to long wavelength macroscopic degrees of freedom. Effective field theories only make sense if we specify what features we're interested in. So I think that's right up to a point. We do need to specify that the variables we're interested in are, in fact, the macroscopic ones, and that's necessary for the RG scheme to work for systems that exhibit behaviors at different scales, especially if we're interested in the ones at higher scales. But I think that's quite different than supervised learning, where one needs to tell the algorithm what counts as a success, whether the image is in fact a cat, for example. So it seems like determining correlational features in a representative volume element, whether through dart throwing or examining molecular pileups, does not require that we know the nature of the correlations in advance. And so I think machine learning RG approach to finding correlational structures might be successful because it's implementing this Kadanoff and Martin field theory inspired approach to many body systems. So I'll stop there. Thank you.